get. Okay, in Gay-Lussac, we're going to have one condition. Okay? In this case, we're talking about a gas, okay, in a container at a pressure of 325 atmospheres at 21 Celsius. According to the directions that the container has, it says that it's warning the user not to keep it in a place where the temperature exceeds the 75 degrees Celsius. What would be the gas pressure in the container be at 75 degrees Celsius? So, first of all, I need to understand what is the problem given me and what I need to find. And obviously, what law I need to apply. Because sometimes I'm going to give you like the specific name of the law that you have to use, but some other times I won't. Okay? So, let's analyze what is given in this problem. It says that this gas is at a pressure of 325 atmosphere at 21 degrees Celsius. So they are giving me information about pressure 3.25 atm, and they're giving me the temperature as 21 Celsius. These two are going to be my initial conditions. Sorry. Like that. Okay. So how I know these are the initial conditions? Okay, because the gas is stored in a container. Okay, then they are telling you that there are conditions or there are storage directions in the container. I mean, they are warning the user that please do not keep this gas at a higher temperature than 75. So 75 is telling you that is the most temperature that it can be reached. Okay, so in this case, they are giving you hypothetically my final temperature or my second temperature is going to be 75 degrees Celsius. So this is my initial. My actual temperature is 21 and my actual pressure is 3.25. Because of the information that is given me, the problem, and it says what is or what will be the gas pressure in the container. What will be the gas pressure in the container? So that means that I need to find my final pressure. So for the data that the problem is giving me, they are giving me pressure and temperature and pressure. Okay, so basically we are just relating to I forgot his name. Two quantities. We are relating pressure, which is one quantity, and temperature, which is another quantity. Even if I'm giving you more values than just two, okay? But we're just relating two different things, pressure and temperature. So when pressure and temperature are related, we say that we apply Gay-Lussac's law. Gay-Lussac establishes a formula that relates two things, pressure and temperature. So what does he say? That the ratio between pressure and temperature remains constant. That means that the ratio between pressure and temperature in the two moments, initial and final, is going to be the same ratio. Okay? So in this exercise, I'm isolating P2, okay? Which means that I just need to remove T2 from the bottom. T2 is doing a division. So when you move it to the other side, it's going to be doing a multiplication. So in the end, this isolation is going to be T2 times pressure 1 over temperature 1 will be equal to P2. And all I need to do is replace it by our givens. Now, there's another thing that we need to do before working with this problem, and that is to convert the temperature. Remember, in gases, in gas laws, all those temperatures need to be converted to Kelvin. Always, always, always. So we have here this temperature, Celsius. The two temperatures of Celsius are going to be turned into Kelvin. Okay? So, this is going to be plus 273 plus 273 is going to give me the kelvins. So these are 294 Kelvin, and this is, I don't know, 348, I guess?
Yes.
348, okay. Wasn't sure. Let me see something. Sorry, I need to see something. Okay, now that the temperature is already converted in Kelvin, we can continue with the exercise. We're going to replace by our given temperature 2, that is 348 Kelvin, multiplying the first pressure that was 325 atmospheres. All this divided by my initial temperature that was 294 Kelvin. Hopefully you didn't confirm that it was the good temperature, but I assume it's good. I assume I can add. I can mentally add. How much is this? Remember, you have to make sure that the two units of temperature, the two kelvins are going to be cancelled out. So, how much you got here?
85.
3.85. I just heard 85, by the way. Oh, no, mi teléfono. 3.85 ATM. So, the condition here in Lussac is a closed container, okay? A closed container. A closed container that is not allowing the gas to spread, okay? It's not like a freely moving piston that if the gas expands, the piston is going to move. No. In Gay-Lussac, we have the condition that the volume is constant, okay? Here we have the condition that the volume is constant. Another thing to say about Gay-Lussac is that because the volume is constant and inside the container you have the gas where the temperature has increased, that increase of the temperature will cause the particles to move faster. Moving faster increases the internal pressure. So let's analyze if it makes sense. At a lower temperature of 21 Celsius, we had a lower pressure. And at a temperature of 75 degrees, I expect to have a greater pressure. And that's exactly what happened here. So we analyze our answer and we say, okay, it makes sense. So in here, again, I repeat the isolation process. Just T2 that is affecting my pressure too is the one that is going to be changing the position. And remember, you're going to move it to the other side, to the opposite side. It's going to be doing the opposite operation, okay? So T2 is going to be, it was divided and it goes to the other side to multiply. So the main equation, this is the main equation, guys. This is the main equation. That's what you have to memorize, not the isolations. I can give you all the isolations that you want, but the one that you memorize is the main equation because from there you're going to isolate. As a reminder, all temperatures need to be converted to Kelvin. Okay, in the combined gas law, as the name says, it is combined. That means that we're going to combine all the laws that we know so far. And the laws that we know, we are relating pressure, volume, pressure, temperature, volume, temperature. So what happens in combined, we're going to be relating all of it. Okay? Now, how do I recognize if I have a combined gas law to apply? Because of our given. First of all, in this exercise, it says 500 milliliters gas sample at STP. Do you remember what STP means?
Standard temperature.
Standard temperature, and P stands for what?
Pressure.
Pressure. So, 500 milliliters gas sample at STP, which means standard temperature and pressure, is compressed to a volume of 200 milliliters, and the temperature is increased to 35 degrees Celsius. What is the new pressure of the gas? It's said to be in pascals. Okay, so in this kind of exercises, we need to be aware of exactly what STP means, not just knowing that it's standard temperature and pressure, but also knowing what the standard temperature and the standard pressure are. Okay, so as I told you the other day, scientists have agreed that the standard conditions are going to be 1 atm of pressure and 0 degrees Celsius of temperature. So when we say STP, remember, STP means 0 degrees Celsius and 1 atm. So saying that storing a gas at STP, that's what it means, okay? 0 Celsius and 1 atm. So knowing this, we're going to start writing the givens. So this sample, initially, what was the volume? What was the initial volume of the sample?
500 milliliters.
500 milliliters. So initial
500.
500 milliliters. What is my initial pressure? Initial pressure is
1 atm.
STP. That means 1 atm. What is my initial temperature? Again, is STP. What is my initial temperature?
0 degrees Celsius.
0 degrees Celsius. Okay, now we already have the initial conditions. What about final conditions? Do I have a final volume?
200.
100 milliliters. Do I have a final pressure?
No.
No. I need to find it. Do I have a final temperature?
35
35 degrees
degrees Celsius.
Celsius. So, first things first. If my temperature is in Celsius degrees, I need to convert to Kelvin. Okay? So, easily, we convert to Kelvin. Plus 273 plus 273. Okay? So, my initial temperature is 273 Kelvin. And my final temperature is 308. 308? Yes? No? Should I use the calculator to? Yes, I will. I better do it.
Yes, 308.
308. I need to be more confident. So sometimes I get confused in the silly things. Okay. Temperatures already in Kelvin. But there is one condition that the problem is telling you about the new pressure. What is the condition for the new pressure?
In Pascal.
That have to be in Pascal.
It has to be in pascals, okay? In pascals. So I need my initial pressure also to be in pascals. So how do I convert from ATM to pascals? I need to convert from 1 ATM to pascals. What is the conversion factor? And I said pascals, not kilopascals, which are different.
1.013 times 10 to the 3, not to the 5.
To the 5. Yes, to the 5. Okay. So we say that in 1 ATM, we have 1.01325. I don't remember the number that you gave me. I guess you only gave me 1.013.
Alright, that was okay.
201, right?
I prefer to use the full value, but
101,000 also.
I prefer to use the 101,325 because for me it's easier to memorize like that. But anyway, both ways are correct, okay? Both ways are correct. I prefer to use the other value though. 101,325 pascals. So you cancel out, so it's gonna give you the same number, okay? Because you're just multiplying times 1. What a horrible 101. 101, 325 pascals. Okay, so your initial temperature is actually 101,325 pascals. So this is your initial pressure. What do we need to do now? Because I see volume, pressures, and temperatures, I know that I have to use combined gas law, okay? Because I see all those values. So gas law, the combined gas law is, okay, I'm going to write it here. Combined. In combined gas law, we're going to have this formula, okay? We're going to have pressure volume in the top, okay? Like the first equation that I gave you, boils, okay? Pressure 1, volume 1, but all this now divided by the temperature 1, equalized to the same but 2. Pressure 2, volume 2, divided by temperature 2. My unknown is pressure 2. So I'm going to need to isolate. First of all, I'm going to send temperature 2. Well, it doesn't really matter, you know. Every time I teach you how to isolate, I think, is there a better way to do that? But in the end, it doesn't really matter. It's the same. Okay, anyway, so T2 is dividing, so it's going to go to the other side to multiply. So you will have T2 times pressure 1 times volume 1, oh beautiful, divided by temperature 1 equals pressure 2, volume 2. Still, you are isolating for pressure 2, which means that volume 2, that is multiplying, is going to go to the other side to divide. Okay? So you will have T2, pressure 1, volume 1, all this divided by volume 2 that was multiplying and came to divide, and temperature 1 that was originally there. So my equation is already isolated for pressure 2. All I need to do now is replacing by our givens. So my temperature 2, that is 308 Kelvin, multiplying my pressure 1, that is 101 3025 pascals, volume 1, that is 500 milliliters, divided by temperature 1, that was 273 Kelvin, also divided by the second volume, the volume after the compression, that was 200 milliliters. So you cancel out Kelvin with Kelvin and milliliters with milliliters, leaving your pascals alone. All this is equal to pressure 2. How much is this?
285,788.46.
Okay. Okay. 285,788.46 pascals is my final pressure. Again, for combined gas law, the main equation that you have to memorize is the first equation from here, from the top. Okay, that main equation. Eunice,
Yeah, I know what my mistake was.
okay. Yes, please, don't commit that mistake. It's very sad because I see all procedure good, but the answer incorrect. And that makes me sad because, oh no, what a silly mistake it was. So, remember, and when we talk about pascals, it's a large number, okay? This is not a decimal point, so I'm going to remove it. This comma, I'm going to remove it. I think that's better. So in combined, as I told you how to recognize combined, because the three quantities are going to be related: volume, pressure, and temperature. And this one, in honor to the quiz, from the week 9, okay? Partial pressure, and I still wonder why. Okay, in the table of water vapor pressure, tell me what is the pressure of water at 24 degrees Celsius in torr or in millimeters of mercury, please. From the table, we obtain that the pressure of water by vapor at 24 degrees Celsius is what?
22.4.
22.4. Jesus Christ. 22.4. These are millimeters of mercury. And as I told you, millimeters of mercury is the same as torr. Well, they are equivalent. So you can say that these are 22.4 torr. Okay? Impartial pressures is Dalton's law of partial pressure. In this law, we're going to have the formula is quite simple. Okay? Um, The total pressure of a mixture of gases is equal to the individual pressures of all the gases that are making up the mixture. How many gases I have here? Oxygen, carbon monoxide, carbon dioxide, and nitrogen, and water vapor. So 1, 2, 3, 4, 5 gases, okay? So I'm gonna have pressure of water, pressure of oxygen, pressure of carbon monoxide, pressure of carbon dioxide, and pressure of nitrogen gas. The one that the problem is asking you to find is what is the partial pressure of oxygen? So this one is your unknown. So when you need to find partial pressures, all you need to do is from the total pressure of the mixture, okay, or the total pressure, you're going to subtract the rest of the gases. So minus water, minus carbon dioxide, minus carbon dioxide, minus nitrogen. Okay? Okay. Italian City. I didn't want to call you. Okay. Now, all you do is replace them by the givens that you have. 22.4 torr. Sorry, this is total. The total given in the formula is 775. Well, those are also torr. Minus 22.4 from water. Minus carbon monoxide, that is 100 torr. Minus CO2, that are 25 torr. Minus nitrogen, that is 505 torr. How much is this?
122.6.